begin with our next talk. So Tomohiro Sasamoto. It's our first talk from Japan, actually, I think, right? So
Really?
you can see he's titled Exact Density Profile and Current Fluctuations in a Tight Binding Chain with Dephasing Phase. Thanks a lot.
Thank you for the introduction, Mireille. First of all, I'd like to thank the organizers, Mireille and Bajanov, maybe others, for giving me an opportunity to give a talk on this very special occasion. And today I'm going to talk about this subject, which is based on a joint work with Taiki Shiyama, who is my PhD student, and Kazuya Fujimoto, who is my younger colleague in the same institute. Okay, so and there are already two references. So if you are interested, please take a look at them. Okay, so first, let me talk a little bit about some main messages of my talk today. So yeah, so this is a very special occasion. So I looked at the Wikipedia again, and almost at the beginning, it was written that Professor Rodney Baxter was an Australian physicist specializing in statistical mechanics, and I think this is certainly correct. So, yeah, we have to check whether this is correct or not. This is in Wikipedia, and I think this is correct. And he, of course, he received a Boltzmann Medal in 1980, and then Wikipedia writes that he is well known for his work in exactly solved models. And I think I completely agree with this. I think this is correct too. But here I want to make a little point. So I think in his case, the models, exactly solved models in this exactly solved models refer to the models in equilibrium statistical mechanics. And maybe I haven't checked all papers of Baxter, so maybe there are some papers on non-equilibrium statistical mechanics. So if somebody knows about his works, maybe I'm curious, so please let me know. But as I said, he received the Boltzmann Medal in 1980, and I think one of the biggest contribution was the exact solution for the 8-vertex model. And the paper appeared in 1971, right? And of course, in the 60s and 70s, in statistical mechanics, the kind of biggest problem, the biggest theme was the phase transitions and critical phenomena for equilibrium statistical mechanical systems. And yeah, there are many questions and so on. And the exact solution for the 8-vertex model by Baxter. So this provides various insights and understanding for this. So this was very big achievement around the time. But I would say that, yeah, the frontier of statistical mechanics has shifted from equilibrium to non-equilibrium in the 80s and 90s and so on. And this is still continuing. So then one question is that what about exact solutions for non-equilibrium statistical mechanics, right? So, and my main message today in this talk is that, in fact, there are some or even many non-equilibrium statistical mechanical models which have been solved exactly. And the reason why they can be solved is still basically thanks to Yang-Baxter equation or relation. So in that sense, we are still relying on, the legacy of Baxter, but there are some a bit different aspects from the real works of Baxter and some new developments, I think. And in my talk, yeah, even though my kind of main subject is about recent exact solution for quantum mechanical model, maybe by using the first 10 minutes or so, I want to explain some these kind of developments for a first for a few classical stochastic models, and then I explained about my recent work with my younger colleagues. Another point maybe I want to make at this point is that, of course, I think people here are very much interested in integrability, and in particular the Yang-Baxter integrability. And I also love it, and this is very beautiful and fascinating. But I'm more from the statistical mechanical side, and in statistical mechanics, this is part of physics, and of course, computing physical quantities are most desired. And of course, Yang-Baxter equation is also related to high energy physics and also some mathematical physics and so on. And in some cases, so you're finding mathematical structure. This is already very big advance and very important. But from the point of view of physical, statistical physics, we want to compute some physical quantities, I think. And of course, as you know, many of the Baxter's works reach this point of calculating really physical quantities. And a question is, what about the non-equilibrium models? And I will explain a little bit that this kind of goals of computing real physical quantities have been also achieved for a few non-equilibrium models. Okay, so as a personal recollection, I'm getting old. So in 1995, I became a PhD student of the group of Professor Miki Wadachi. And since then, I have been working on exact solutions in non-equilibrium statistical mechanics. And I met Professor Roderick Baxter a few times. And one time was in, if I remember, I think it was 2001. He visited the group of Wadati, and there were some few seminars, and we also went to party and so on. And yeah, I don't have a strong personal interaction with Professor Baxter, but each time I saw his paper and I met him, I was always very much impressed by his scientific depth, of course, and also by his very gentleman behaviors, kind of British behaviors. Okay, so let me go on. So this part is for maybe many of you almost a bit trivial, but still let me explain this basic part for those who are not so familiar with the subject. But still, so let's start from something which should be known to everybody here. So let's start from the Hamiltonian for the Heisenberg spin chain isotropic case. So S is Pauli spins, or maybe 1/2 of them. So this is the XXX Hamiltonian. And maybe one notices that if you represent by maybe Pauli matrices, so all off-diagonal matrix elements are non-negative. Most, non-trivial ones are all positive. So then, maybe just by adding a constant, one can see that this Hamiltonian becomes stochastic matrix, which means that if you write this Hamiltonian as a big matrix, then if you look at the each column, each row, maybe the opposite, each row, and if you take a sum of the matrix elements of over all columns, then this becomes 0. So off-diagonal elements represent some transition, can represent some transition rate from one state to another. And the fact that the sum is 0 means that there's a conservation of probability. So in this way, so this Hamiltonian, quantum mechanical Hamiltonian for the Heisenberg spin chain can be also understood as a generator for stochastic process, Markov process. So this, I mean this stochastic by this fact. Okay. And so for this Markov process corresponding to the Heisenberg spin chain, this is a well-known model in non-equilibrium statistical mechanics, also in probability theory, and this is called a symmetric simple exclusion process. Here I abbreviate it as a SEP. So the model is like this. So we consider one-dimensional lattice. Each site is either occupied by a particle as empty, and all particles try to do symmetric random walk, but there are exclusion interactions among particles. So yeah, there could be only at most one particle at each side. So this is a very simple Markov process. But this is one of the standard models in non-equilibrium statistical mechanics. Okay, so as a interesting and important generalization of this symmetric exclusion process, there's something called ASEP, which is an abbreviation, asymmetric simple exclusion process, in which this is more or less the same as the case of SEP, but now each particle tries to hop asymmetrically. So maybe with rate p to the right and with rate q to the left, right? But the exclusions are the same. And one can think about the stochastic or Markov time evolution of these particles. And in this case, one can also represent these transition rates as a matrix. And you may notice that this is not Hermitian. So this is different from the kind of standard quantum mechanical system. But this has a different meaning from the point of view Markov process. And one can, in fact, see maybe modular boundary conditions. This is a little bit tricky part, but basically, generator of A set is similarity transformed to the Hamiltonian of the XXC spin chain written here. So in this way, quantum mechanical Hamiltonian, in particular the spin chain Hamiltonians and Markov generators of certain interacting particle system, they are sometimes exactly equivalent, or they are sometimes related by simple similarity transformation. So eigenvalues are the same, and eigenfunctions are related in a similar way. So then you may think that maybe just by importing some techniques from exact solution for XXC spin chain, one can just solve the A set simply, right? And this is part of true and not exactly true, as I will explain a little bit. So this kind of correspondence between quantum mechanical Hamiltonian and Markov process generators in non-equilibrium statistical mechanical models. So they have been noticed, this has been noticed in the 90s mainly. Some people noticed in 80s, but I think there are more people who realized this connection. And one particular a group of people who noticed this connection was Alcaraz, who is here, and Henke, Rittenberg, and so on. Okay. So then the story may sound quite simple, but there are simple but very important differences between the two cases. So first, the time evolution is a little bit different. In quantum mechanics, the standard time evolution is, of course, Schrödinger equation given here. And in the case of stochastic process, in particular the Markov process, so time evolution is described by the so-called master equation, which can be written in this way. So, as I said, the H is usually is a Hermitian matrix, and M should be stochastic. Sometimes they are different. This is one difference. Another big difference is the existence of I for the quantum case and the non-existence of I here. So this is something like a weak rotation. Sometimes this can be done. Sometimes it is tricky, as you know. And so this is different. But formally, they are very similar at this level. But maybe more important differences are the physical quantities, how we calculate the averages. In the quantum mechanical case, of course, we kind of sandwich the physical observable by the same state, like this. So this is quadratic in psi, which is evolving according to the Schrödinger equation. But in the stochastic case, the average is linear in probability. So one is some particular vector with all components equal to 1. And the way we take the expectation for stochastic model is to compute this kind of matrix element, which is linear in P. And somehow, so this difference makes like rather different. So for us, when we do some calculations, somehow the two cases are very different. Okay, so let me mention one particular example from the non-equilibrium statistical mechanics is the Kardar-Parity sign equation, KP's equation. Of course, for some of you, another KPZ may be more interesting or important, but so here we are talking about KPZ, which is the Kardar-Parity sign. So this is a model of a stochastically growing surface. So this is in non-equilibrium. And we consider height function h in 1D. And then the equation is given here. And this describes the time of evolution for this height, right? So this is the diffusive part. This is nonlinear part. And there's also noise, which is taken to be Gaussian in this case. And this is one of the standard models in non-equilibrium statistical mechanics. And so this one of the inventor of this model, Kardar, received the Boltzmann medal this year, just 2 months ago in Florence. So you can see that, so this KP's equation is considered to be very important. Of course, he has different contributions, but this is also an important contribution to statistical mechanics of Kardar. Okay, and so there's a kind of a book about this subject of growing interface by Barabas and Stanley, 1995, but 10 years later, after the Kardar-Parity equation. And as they wrote in a particular chapter related to the KP's equation, that this equation cannot be solved in closed form due to its nonlinear character. indeed, this looks, even though the model looks simple, that this is nonlinear, that this contains noise, so this doesn't seem so easy to solve. But a bit later than this book, after this book, so there was some paper about the connection between ASIP, which I mentioned earlier, and the KP's equation. In fact, if we take certain weakly asymmetric limit in which P and Q comes to close, and we take continuous space and time limit, space limit, then ASIP tends to the KP's equation. And as I said, ASIP is related to XXZ. So then there should be some possibility that the KP's equation may be also solved, right? And in fact, this turned out to be the case. So this is already 15 years ago. In my work with Herbert, and there's another group of people for particular initial condition given by this case, like a wedge, narrow wedge initial condition, there's a nice formula for this particular quantity. H is the solution to the KP's equation with this initial condition, and there are simple shift. And then for this average, this can be written as a single determinant, Fredholm determinant, with the kernel given by this, kernel in terms of Airy function. So this is the story is rather different from the case of 8-vertex model or Ising model. So this is really a result of a collection of works related to these models, starting from Johansson, and there are a very important contribution, Tracy and Willem, and so on. And technically, one way to solve this equation is to use a so-called replica method. And then this turns out to be related to beta ansatz for the delta Bose gas. So this point I don't explain today, but so the problem of KP's equation is related to n particle delta Bose gas on real line. And so then by using this integrability of the delta Bose gas, one can finally arrive at this formula after a long calculation. But the formula suggests that this KP's equation seems related to free fermion at finite temperature. So this was one question. Also, maybe for some people in this, the community of integral system. And then this kind of field has grown into almost a small field called integral probability. There are some names and also important people in Australia. And one a little bit interesting aspect for me is that sometimes stochastic models seems to have even better, nicer structures, mathematical structures or formulas than quantum models. Maybe this is related to difference of the expectations. So there are some nice connections to McDonald polynomials and so on. And one particular consequence for statistical mechanics that sometimes even 2-point time-dependent correlation functions and so on can be calculated. And I think yesterday, Vincent Pasquier mentioned that for quantum mechanical models, really computing time-dependent quantities is still very difficult, but this has been somehow achieved for some stochastic models. And so then one question is ASIP a free fermionic model? And I would say that there's a simple mapping, but so a few years ago, we found one mapping from something related to something called Q-Hitaka measure, which is a bit related to ASIP. And this can be, there's some bijection to free fermion type object related by using Robinson chains to the Knuth algorithm, and this shows some interesting behavior related to box and Bose system, but I don't go into details. If you're interested, please let me know. But as I said, so more recently, there are various developments for non-equilibrium quantum mechanical systems, and in the remaining time, maybe I want to explain our recent example. For the case of the tight binding model with dephasing. So the kind of most standard time evolution for quantum systems is, of course, the Schrödinger equation, which I also mentioned earlier. But in many cases, systems are also interacting with the environment, so we have to take into account the effects of dissipation. And for this kind of case, there are several descriptions, and one rather simple description is provided by the so-called Lindblad equation or GK3 equation for the density matrix rho, which is written here. For those who are not, the H is the usual Hamiltonian, and Lx is called the Lindblad operator, which describes dissipation of the quantum systems. And for those who are not so familiar with this kind of notion, maybe first you can think about the case where L is 0. So then the time evolution for rho is simply for Neumann equation. So now the effects of dissipation is taken into account by putting this term in terms of L, Lindebrand operator. And in our case, we take a very simple case. So we take Hamiltonian to be the free fermion, represent here, so A is fermion. And then for the Lindebrand part, we take Lx to be just a particle number. And the gamma is the strength of the dissipation. Now we consider the time evolution of density matrix according to this G-case equation, right? And the model itself is very simple and has been studied by several people before. And one thing which has been noticed is that if we consider large gamma behavior of this system, this corresponds to set. There's a perturbation calculation, and there are some arguments as well. But for example, for tiny gamma, what happens? So this kind of question is not so obvious to answer, but this is something now we can try to understand by exact solutions. Okay, so as quantities, we're interested in this talk. Maybe one simple quantity is the simply average density profile. So depending on initial conditions, so this density may depend on X. So then we can think about some density profile, right? Which is can be calculated in this way. Rho in is the initial density matrix. So this is time evolution, and this is the number operator of the fermion at X. We are also interested in integrated current, where even fluctuation of the integrated current, which is defined by this, can be defined by this. So NR is the number of particles on the right half of the systems, and if you count the difference of the number of particles on the right half of the system at time t and time 0, so this is integrated current, right? And we are also interested in average and the variance, and also maybe full distribution of this quantity, which may be calculated by calculating this generating function. And in particular, we're interested in variance. Okay, so we also have to specify initial conditions, and in this talk, we focus on rather particular simple case in which density of fermions are rho A to the left and rho B to the right. And as a density matrix, this can be represented in this way, where rho X is rho A for the left and rho B for the right. Okay. Okay, so even though we consider general two-density situation, in fact, the problem can be reduced to a much simpler case of 1-0 situation, because we can show something called omega dependence for this model. So this means that so this generating function we are interested in can be represented as a series of a little n, and then the summand is a product of something we call Qn of t, and then omega to the power n. And this omega is defined in this way in terms of the two densities, rho A and rho B, and the parameter for the generating function lambda. So if we take this particular combination of these three parameters for the generic case with rho and rho B, so this generating function can be expanded as a series in omega, right? And then, so the remaining part, Qn, can be represented as the sum of n particle density matrices, so written in this way. So this is a matrix element, and if we can find some formula for this, then after that we should take sum over x and y. Okay, so a point here is that originally we are thinking about, so this free fermion on with a dephasing system for finite density situation containing infinite number of particles. But so this omega dependence reduces the problem of finite density to a finite number of particle problem, right? So this is a huge simplification of the problem, and we can exploit this fact to solve the problem. And in fact, a similar reduction has been also observed and shown. But for the case of SEP, this was shown by Derrida and Gershenfeld. And this is in fact also related to the fact that which I mentioned already for the KP's equation. The KP's equation, I said that can be reduced to the problem of n particle delta Bose gas, and in fact, they are more or less the same thing. Okay, so then the point is that this Green's function satisfies closed equation, and this can be solved. But to see a connection to well-known model, maybe we introduce some notations. So this part is maybe a bit heavy, sorry. But as a slight generalization of the object here, we can define the Green's function in this way. So then this QNT, which is of very importance, this can be written as a sum over this. And then, so we want to consider this Green's function, but to see a better connection to a well-known model, maybe it's a bit useful to modify slightly by multiplying with a simple object here. Then we call it psi. Then, so there are some small remarks, but I'm running out of time, so let me skip. But anyway, so for almost like a Green's function, we can see that it satisfies the Schrödinger equation in this form. And this Hamiltonian for this n particle system is written in this way. And as some of you may notice, so this is just the Hamiltonian for the n particle Hubbard model with imaginary coupling. And of course, the Hubbard model is a well-known quantum integral system, and even with imaginary coupling, so one can try to use this fact to solve the original problem of free Fermi with dephasing. And this fact itself was already noticed by these people almost 10 years ago, but they used already the beta ansatz and discussed some, rate of the convergence to equilibrium and so on. But they started from finite ring and they used the beta ansatz equation. With this way, I think it's still a bit difficult to really calculate the physical quantities, but now we are considering a system on infinite line from the beginning, and this helps to do the actual calculation of physical quantities. The initial condition is simple delta, and the point is that, so for this quantity, Green's function or wave function after slight modification, if we consider a system on Z from the beginning, we can write down the quantity as multiple integral explicitly, exactly. And we can actually prove it. And the formula is not so complicated. E is just coming from the energy, and phi looks a bit complicated, but at least for small n, this can be calculated exactly, explicitly. One point is that to satisfy the initial condition, so we have to take these contour integrals appropriately, and this contains some nesting condition. This part is a bit non-trivial, but this can be done for our case. And in fact, this kind of formula has some analogs in the case of the classical stochastic processes like ASIP. So this was found by Schutz, Tracy Wilson, and Polodin, myself, and so on. And we can think that this formula for our quantum mechanical system can be considered as a nice quantum generalization of such formulas. Okay, and then once we have such exact formulas, we can take a sum to find some exact formula for Qn. So this is still a bit complicated, but recently, so Taiki, the student, is making progress to make it simpler. But for the moment, we are using this formula, and but we can still do some asymptotic calculations with these. And so now we come back to the physical quantities for exact density profile. So here I'm showing just the case of domain world case, 1-0 case. In this case, we could find the exact formula in terms of the Bessel function in this way. There's a nice reductions to the known cases. And so by using this, we can simply calculate average integral current. And by using this, we can study long time behaviors. It shows nicer this curve. And long time behavior turns out to be exactly given by SEP. But we can also, because we have exact solution, we can also study the correction to the behavior of SEP. There are some nice arguments, not completely, for more general models, there's a similar argument by Esra and the collaborator. we can, by using the same formulas for the n equal 2 case, we can also study the current fluctuations. So we can also see the behavior, long-time behavior of the current fluctuation variance. This is given by this. So basically, this is this turns out to be the same as SEP again, as a little bit expected. But for tiny, so this appears even for tiny value of gamma dissipation. So this has become possible because we have exact solutions. Okay, so this is what I wanted to say. So the main messages are here. So some non-equilibrium statistical mechanics have been exactly solved, again, thanks to this Yang-Baxter equation. And there are some differences. And this, why there are such a difference, and sometimes stochastic models have even better structure. This is still not completely well understood, and this is an interesting question, I think. And there are some recent progress for non-equilibrium quantum mechanical models and reported on our exact recent result. Thank you for your attention.
Okay, do we have any questions for Tomohiro?
I mean, probably online.
Murray, can I perhaps ask a question? It's Ollie here. I'm online.
Go ahead.
Yeah, thanks for a very interesting talk. So you mentioned that the ASAP model is related to XXZ. So if
Yes.
do we get some similar model that's related to XYZ?
XYZ, yes. Recently, there's a paper by Schut and so on. But maybe, sorry, for general case, I'm not completely sure. But recently, the Schut et al. was studying some, at least some particular case of XYZ. And this is also related to stochastic models. And one can discuss various interesting critical phenomena. Maybe I can send you some reference later.
Okay, thanks.
Thank you.
I have no questions at my end, so then no other questions here. Let's thanks.
Thank you very much.